Okay, so I started to discuss compatibility, which plays a big role because of this gradient structure. Oh, by the way, I had a question while in the break that somebody was asking whether this device of SunAmp is not an energy conversion device. It's just a heat storage device. So just in case you're wondering, but it fits with the method I'm going to be describing. Okay, so I want to avoid long slides of equations. So, and in fact, this theory can generate long slides of equations. So I'm going to invent a notation, which is a very, very short notation for very long equations. Here's the notation. So, and this goes throughout my lectures. I'll use this notation again and again. That's a circle. A circle is SO3, all rotation matrices in 3 dimensions. So identity is a rotation matrix. Well, first of all, the slide is 3 by 3 matrices, okay? Or tensors on R3. There's the identity, of course, is in SO3. So of course, if it was SO2, I mean, in 2 dimensions, the circle is very reasonable for SO2, but for SO3 is a 3-dimensional manifold sitting in 9-dimensional space. In fact, with corners on it. So it's not so. But anyway, I'll still use this notation. And if I have a notation like that, of course, it would mean SO3 times A. So all rotation matrices times A. I'll also use this because this compatibility involves rank 1 differences between tensors. I'll use this notation. If I draw a line, between two matrices A and B in R3 cross 3, it means they differ by a rank 1 matrix. It means there exists A and N such that B minus A is A tensor N. So I guess it's kind of reasonable notation. I hope it's not too hard to remember. I'll remind you as I go. So this picture represents, you have 2 matrices given, say, positive definite symmetric matrices U1 and U2. This is SO3 times U1. This is SO3 times U2. In other words, all rotation matrices times U2. This means that B is a rotation matrix times U2. And it means also that A minus B is rank 1. And also I put C on the line between A and B. That, of course, just means that C is lambda A plus 1 minus lambda B, where lambda is between 0 and 1. Okay? So straight lines connecting 2 dots mean they differ by rank 1. Circles are copies of SO3. Okay. So the lemma in that notation is that picture. It says, here's SO3. It says that if the middle eigenvalue of this matrix is 1, it says there's exactly 2 rank 1 connections. There's exactly 2 matrices over here. In other words, if I look at all matrices of the form SO3 times U1, then there's exactly 2 of them which differ from the identity by rank 1 matrix. That's the lemma. So that's the lemma in pictures. So now I'm going to present some results which can get us used to theory of phase transformations. So that's the picture. Let me present an energy function for a particular material. And I chose one material because, first of all, I have lots of pictures of the microstructure of that material. It's a well-known material. But it allows me to show this material through many physical concepts, and so it's a real material. And it has this transformation stretch matrix. It's actually, those are the values of alpha, beta, and gamma. We actually know those very accurately because they're measured with X-ray measurements, and these are very good crystals, so you get very good X-ray measurements. And the symmetry theory that I didn't say much about, which tells you about the symmetries of this phi, says that if U1 is a minimizer of phi at some temperature, then automatically there are 6 such matrices, and there are these 6 matrices. As you can see, they're kind of symmetry related. They are symmetry related. In fact, they're related by conjugation of rotations in the point group of a cubic crystal. That's, but I don't want to go into so many details about symmetry. Those are the 6 matrices. And if I put the transformation temperature, if I put the temperature equal to the transformation temperature, and I look at the 0 level set of phi, in other words, I look at the minimizers of phi with theta, theta c in this variable. So they're 3 by 3 matrices which minimize the phi. In this notation I just made, they look like these circles. So so U1 minimizes phi, and U2 minimizes phi, and all the 6 there's U3, U4, U5, U6. At the transformation temperature also the identity minimizes phi, and this identity, this circle attached to the identity represents the austenite phase, the cubic phase in this material. This other phase is actually an orthorhombic phase, and there are 6 energy wells associated with the orthorhombic phase. So the way you should think about this is there's a surface phi which comes down and touches the slide at exactly those 7 circles, and everywhere else is positive. Okay, that's the kind of free energy density which comes out of those symmetry arguments. Typical free energy density for a crystal which undergoes a phase transformation. If you take theta and you go above the transition temperature, then this well goes down relative to these wells always have the same height, and this well goes down, it goes into the screen relative to the other wells. If you raise the transformation, if you lower the transformation temperature, then this well goes up. So it's a typical first order phase transformation. At the transformation temperature, everything has the same height. Above, this is the lowest well. Below, these are the lowest wells. Okay. And now, if you want to minimize the energy, it's very easy to do it very easy to start doing it by hand. So, for example, you can't do better when you're minimizing the energy if the boundary conditions are consistent with it, to minimize the integrand itself. So if I take the gradient and I try to stick it on these energy wells, then I can have an energy minimizer. That's a way to construct energy minimizer. Energy minimization by hand. So so this 0 level set, these energy minimizers are very important, of course, and the structure of them and these matrices, exactly what these matrices, the structure of these matrices, very important for phase transformations. That's the key. So, for example, if you have an ordinary elastic material like a piece of rubber, it would just have one energy well, whereas this phase change material has all these energy wells. So if you're going to minimize the energy, in fact, all exact minimizers of the energy without boundary conditions, in this case, are described by gradient y is in SO3. And then, by Liouville's theorem, it means that the gradient of y is constant. So, just the regularity given by this equation says that the gradient of y is in fact one rotation matrix. So it's a very rigid situation. In this case, the gradient could lie on any of the wells at different positions, and so it's not so clear exactly what kind of microstructures you can have, or what's the flexibility of a crystal with such and such energy well structure, and how does it depend on the choice of this matrix U1. Okay, so for example, we could do this example. This is that material that I just described, that copper, aluminum, nickel alloy. And it turns out, so you do this calculation. So I'm doing a calculation again, which would take 2 or 3 slides if I wrote it all out. But here's you take any matrix on this well. So A is a rotation matrix times U1. And it turns out, it turns out that this well is compatible with this well. Now, the way I wrote the lemma, this matrix A would have to be the identity, but it's easy to change it, by post multiplication. It's easier to change it to any A. Bottom line is that A is rank 1 connected to exactly 2 matrices over here. Okay? I'll choose one of them, B. And then B, it turns out these 2 wells are rank 1 connected too. So the B is rank 1 connected to exactly 2 matrices over here. I'll choose one of them, C. C is rank 1 connected to exactly 2 matrices over here. I choose one of them, D. And now the magic happens. You know, if I make exactly the right choice of these wells and exactly the right choice of those rank 1 connections, I had some choices, and then D turns out to be exactly rank 1 connected back to A, okay? It's not an usual situation. I mean, if I had, instead of going from this well to this well, I had tried to go to this well, it wouldn't have worked, you know. Or if I had, instead of taking B, I had chose the other rank 1 connection, it wouldn't have worked. So anyway, and what those rank 1 connections mean is that the A and B are compatible across this interface, and C and D are compatible across this interface. And in fact, those 2 interfaces coincide. So in fact, the rank 1 connections implied by those straight lines mean that all these interfaces are compatible. That means the gradient of y can be integrated, and there's a continuous y function y defined on this domain with exactly those gradients. Okay? And then you plot this, now you just take this continuous function, you plot the deformed configuration. It looks exactly like this. Okay? So that's a microstructure. This is not a simulation. This is a observed microstructure in the material, in this particular material, and it's also, there's another form of it right there. And this surface, you know, this surface, because these deformations are all different deformations, this surface has roofs like this. You know, it goes up and down, or it goes up and down like this. So this is not a flat surface. We had a very nice thing in Oleg's lecture yesterday about how the fact that the analog of what he said at one point in his lecture is, if you take this surface and now you polish it flat. You can do that. You just polish this surface flat. It's not flat now because it was transformed from a high temperature phase. It was polished in the high temperature phase. Okay, and then it was transformed, and we got this ripply surface with all these roofs on it. Now you polish it off in the low temperature phase, and you transform back to the high temperature phase. Now the appearance of the specimen will be full of roofs and, you know, atomically sharp interfaces. The surface will be all rippled up in the high temperature phase. It will look like this microstructure, but there's no microstructure because the high temperature phase is just one phase. There's absolutely no interfaces, but it will appear. It's because you're seeing the inverse deformation. So that's what Oleg also mentioned in a different context yesterday. Anyway, that's a nice confirmation that seems to be we have the right energy wells, at least in this particular situation. Was there a question back there? Yeah.
I was just hoping you could link the diagram to the picture.
Yeah.
Is what happens in the picture explained by that diagram?
It's exactly explained. It's in detail. You know, I didn't actually. I could have done this, but. So the diagram justifies this picture where every single interface is compatible. This is a picture in the reference configuration. This is the domain omega. And now you take these deformations and you integrate up to find the function y. Then you take a polished surface, you know, you take a flat surface and you apply y to that flat surface. It will produce that picture. With all the surface relief, all the angles will agree perfectly with that picture. Even at atomic level, the structure of the lattices will agree back through the Cauchy-Born rule with that picture. Okay? Yeah. So good question. So you have to be careful because this diagram and this is in the reference configuration. So this gradient y, where it's Lagrangian formulation, so it's a function of x. X belongs to omega. This is omega. This can be thought of as the austenite, but if you superimpose, you compute this deformation, look at the deformed configuration, you see what's in the picture. Yeah, yeah.
Given these 6 U's, can I always find A, B, C, and D that they form this cycle?
Yeah. This is, so that's a good question. This is independent. This is a symmetry thing. If you have, so I had these energy wells, let's see, where are they? There. So this is a feature of the symmetry. It does not depend on any special choices of alpha, beta, and gamma. Any alpha, beta, and gamma will give you this possibility. On the other hand, as I said, you have to choose the wells correctly. You have to choose which rank 1 connections. You have some choices. You have to make the right choices. Yeah. Is that clear? Is that clear? Yeah. It's not something about special lattice parameters, which we'll get into later. Okay, this is for mathematicians in the audience. This is quite interesting thing. So, okay, now forget everything I was just saying. We're going to do a calculus problem now. We're going to define the function f. F of x is x squared if x is not equal to 0. But f of 0 is 1. Okay, so we'll define this function, which is missing the point 0, and its value at 0 is 1. Okay, and now you minimize this function f using ordinary calculus. Of course, as you can see, it doesn't have a minimizer, because if x is small and x is a minimizer, then x squared is less than x, so that can't be a minimizer. And of course, it can't be 0 because f of 0 is 1. Stupid. But, so that's an example of non-attainment. Okay, there is no minimizer of f. Okay, this functional that we've been using, in fact, we just discussed. If you choose various boundary conditions for this functional, it has the same property. Okay? So it does not, and it doesn't mean that, it could have that property, when you start minimizing in the calculus of variations, you have to worry about which space you're in, which functions you choose, but the most general set of functions which would make sense in terms of the gradient and in terms of the growth of phi would not give you would not have a minimizer of this problem. Okay. The truth is we know, even though people have worked on this quite hard, we know some choices of boundary conditions where this does not have a minimizer, exhibits this non-attainment. But little is known about this case. So we'll discuss what the implications of non-attainment are. So, you would think, so the point is, you take this functional, it's all smooth. There's no nonsense like taking this 0 out and moving it up. This is completely smooth function. Strong growth at infinity, so nothing is escaping to infinity. And this happens. So if you're familiar with basic calculus variations, you might think you solve the Euler-Lagrange equations and maybe check the second variation, and then very likely it's a minimizer of this problem. But that's not true, because it doesn't have a minimizer for many choices of boundary conditions. Okay. And there are physical implications of that I'll describe. Okay. This we already discussed is the low hysteresis. Okay. Now let's see. I wonder. Okay, since my lectures are a little bit jumbled now because of where I stopped, let's. Okay, this is now basically lecture 2 we're getting into here. So I described hysteresis. In one of these phase transformations, think of this horizontal axis as temperature. There's a high temperature phase. This is a very simple cubic to tetragonal phase transformation. The transformation temperature is theta C. In fact, there isn't a single transformation temperature. As I mentioned, is hysteresis. So if I cool this crystal, it transforms here, and then on the way back it transforms there. Even if I go from one variant to another by applying stress, this is a case where by applying a biaxial stress, one variant, it was a single variant here, and then this variant, and then it transformed. There's also a hysteresis loop there. So even though they're the same phase, they're just two variants of the same phase, there's also a hysteresis loop. And the reason I put this diagram there is this was measured with a period of the loading of 10 seconds, 40 seconds, 200 seconds, 1,000 seconds, so varying by 2 orders of magnitude. And the hysteresis loop was very much the same. So that's That would also be true here if I transform back and forth at various periods. In fact, if I transform very fast, I would get a little bit bigger hysteresis loop. That's understood. It has to do with the fact that it takes some time to get the heat in and out of the material. That has to do with that aspect. But if I went, on the other hand, slower and slower, this loop would not shrink to zero as I go slower and slower around the hysteresis loop. That means that hysteresis in these phase transformations is, from a mathematical modeling point of view, it's not caused by some kind of viscosity or viscoelasticity. Because those kind of features in differential equations would have the property that if you went slower and slower around the hysteresis loop, it would collapse to zero. So it must be some kind of other explanation beyond, like the viscosity in Navier-Stokes. You can set up, a cyclic, deformation of a fluid, and you would see that property. But this case is different. It's called rate-independent hysteresis, in fact, this phenomenon. Okay, so since the energy conversion devices very strongly depend on having the smallest hysteresis as possible, we need to face hysteresis. So the main ideas I want to discuss approaches to understanding hysteresis. One classic one is the pinning of interfaces by defects. So you have an interface between the two phases, and inevitably in the material there's some non-transforming defects. And the interface comes up against this defect, and it requires, maybe by your lowering the temperature, you're making one phase more favorable, lowering its energy well by controlling the temperature. And when the interface comes up against this defect, it's non-transforming, and it requires an additional lowering of the energy well of this phase, or an additional lowering of the temperature to cause this interface to break through somehow. There's theory of this, and I describe it in a very physical way, but there's also mathematical theory of this type of situation. And it happens both ways through the phase transformation. You can imagine that this can give rise to hysteresis. Another very standard idea is, which is very relevant in soft materials, in fact, is thermal activation. It's also relevant in plasticity and other areas. And I'll describe that again in a mathematical way. Imagine you have the potential energy, not the free energy, but the potential energy of the system, and I, facetiously plot it versus the positions of all the atoms in the system. Okay, so there's many, many axes down here. People believe this is a very oscillatory graph, very wiggly graph, and in fact, the low temperature phase that we discussed, the Martensite phase, is thought to have very steep energy wells. And you can imagine starting off in one of those energy wells, the system is in the Martensite phase, and of course it starts sitting at a single point. It's moving around here because maybe you could say subject to the equations of molecular dynamics. So the system is represented by a moving point, and then at some point it moves around so much that it transforms. In other words, it comes out of that energy well and sits over here somewhere. It might even sit on average, not in a valley, but on the top of a mountain. That would be called entropically stabilized austenite. Okay, so it could be sitting on top of a mountain on average here. In any case, you start now lowering the temperature. And you can think of controlling, in the mathematical problem, controlling the initial conditions. So you can start lowering the temperature. And eventually you fall back into this well, or one of these other wells associated with the Martensite phase. But you can, as you can easily imagine from this picture, it might be much more difficult for the system to find its way back into this energy well than it is to get out of the energy well in the first place. And that could give rise to hysteresis. That's like thermally activated mechanisms for hysteresis. So both of these ideas are very different ideas, could be relevant. Either one could be relevant, but actually I'm going to tell you a third idea we feel is even more relevant. Oh, okay, that was the end of the first lecture. Okay, now, but I anticipated that there would be a little bit of overlap there. Okay. Now we go to lecture 2. Okay, very good. And we have some introduction here, and there's lecture 2. And I think I discussed this already, and this, and this. Okay. Okay, and we also discussed the model for the free energy for this material. So now I'm going to begin trying to address this issue of what causes hysteresis. Okay. So I'll use this to address it. I'll use this alloy again because I can use a single alloy throughout this lecture, and you can become familiar with this alloy. It's not a particularly good alloy for energy conversion. Yes?
Can I ask you something really simple?
Yeah.
Can you explain one more time why you need low hysteresis?
Oh, you'll see that later. I haven't explained that. So that will be in the last 2 lectures. So that is the main source of loss in the material. Yeah. Yeah. So I haven't explained. The reason you don't know it is because I haven't explained it. Okay. So there's this material. I already discussed it. There's the lattice parameter, so forth. What's going to play a big role in this hysteresis is this microstructure. So this is a microstructure which consists of both austenite and martensite. This is a microstructure you see near the transformation temperature. And it looks quite special and quite unusual, but it's highly generic. In materials that undergo solid crystalline phase transformations, you see it very often. Not in all cases, and I'll tell you why not in all cases, but certainly in all reversible martensitic phase transformations or in crystalline phase transformations, you will often see this microstructure. So what is the microstructure? You see it at the transformation temperature. This, as it's labeled, is the austenite phase. In this material that I'm following through the lectures, it's a cubic crystal structure. These are 2 of the variants of martensite. So the deformation gradients in these bands here fall very near 2 of the energy wells of the 2 of the martensite energy wells. So these are 2 variants of martensite. And this is a classic microstructure called the austenite-martensite interface. When it was first observed, it attracted a lot of attention because, of course, it's a beautifully planar interface. And people measured the normal to this interface, and they expressed the normal in the lattice vector basis of the austenite phase, the cubic basis. And they found that now they expected the normal to have numbers like 2, 5, 3, or 7, 1, 2. But it was 23, 37, 25. I don't know if it was that, but it was. And material scientists call that kind of interface irrational. It doesn't seem to have anything to do with the crystal structure of this phase. Okay, so that was a very big puzzle in the early days. In the early days of martensite, is to have such a beautifully planar interface bordering austenite that seems to have no relation to the crystal structure of austenite. I'll explain why in a second. Okay, so how do we understand this microstructure? We understand it in this way. So I'm going to try to understand it by energy minimization, again by hand. So let's focus on the left-hand side of this picture here, down here. And that's 2 variants of martensite. So I'll take a deformation gradient, and I'll put it on 2 of these energy wells. Maybe this well, the well associated with this one and this one. We have these free rotation matrices. And I'm going to write it this way. That's a convenient way to write it. And we know that that's compatible if and only if these 2 matrices differ by a rank 1 matrix, and the deformed configuration would look something like that. Oops. Oh. And we know how to calculate that. So it's a slight modification of the lemma I presented earlier. And it turns out that for this U1 and this U2, or in fact it could be other pairs, any pair actually, then there exists an R such that these differ by a rank 1 matrix. The R hat doesn't matter because it pre-multiplies the whole equation. So there exists exactly 2 R's. So in some sense, up to overall rotation, there are 2 solutions to this equation. I've pictured one of them here. And everything's measured, so then you go to this structure. You look at the deformed configuration like I've looked here, and you compare with this picture, and it agrees perfectly. even at atomic scale, it's usually in Cauchy-Born rule. The atoms are in the right positions relative to the interface and so forth. Okay, so that explains, and they have a twin relation, there's twinning and so forth. It doesn't matter so much. Now you take the following. You take the solution I just described, and I just described a single interface, but you can layer it back and forth. It still satisfies this compatibility condition. Allow this layer to have, so F is going to describe the volume fraction, as you can see. And I independently want to describe the volume fraction F and the fineness of the microstructure, which is described by the K. As I let K get larger and larger, it gets finer and finer. Changing F changes the volume fraction of these two twins, two bands. And since I've allowed a rigid rotation, this R over here, I just put the gradient equal to the identity here, which models the austenite phase. And you quickly see, I mean, everything here is determined. You quickly see that you cannot have compatibility of the austenite with these individual variants. So I could not just draw a line here and satisfy the compatibility condition. But on the other hand, I simply can interpolate. Here's a deformation. It's now known. I've integrated this up. There's a deformation here. There's a deformation here. I interpolate them across this layer. And so there's a transition layer in here which involves gradients which are not on any of the energy wells. You'll be forced to use all kinds of other gradients. And here's the deal. The deal is that if I make this interface, if I put it at just the right orientation, and I make the volume fraction just right, then I can drive the energy in this transition layer. Remember, it's not on the energy wells, but I can drive the energy in this transition layer to 0 by sending K to infinity. Okay? This is somehow related to this non-attainment, because I've described, therefore, a minimizing sequence. Even though it's using gradients which don't lie on the energy wells, I make them disappear in the limit as K goes to infinity. Okay? Now that requires some conditions. I mean, the R hat has to be chosen also right, and as I said, these other things have to be chosen right. So you work this. This is algebra that I'll talk about later. Anyway, at the end of the day, you can compare with experiment, and the most striking thing is to compare the normal. I said this interface has to be chosen very special. Then you compare the normal to this interface to the measured normal, 37, 45, 23, whatever it is, of this irrational interface, and they agree beautifully. Okay? So that's a great success. It's called the crystallographic theory of martensite. I'm describing it from the point of view of energy minimization. Okay, very good. Okay. So one interest is in this thing, the way this experiment was done, you take this crystal of copper, aluminum, nickel, you stick it on the table, you stick it on a hot plate, and you just cool, or you heat it up, and then you cool it down, you see this microstructure, it sits there. But from the point of view of energy minimization, that corresponds to taking no boundary conditions. You would just be minimizing this energy. So, of course, minimizing this energy, if we take theta and put it at the transformation temperature, that theoretical problem has a solution all austenite. Okay? But you don't see all austenite. You see this. Of course, you can see all austenite, but you often see this mixture of the two phases. And so that means the first remark is that so this problem from a mathematical point of view has a minimizer. It's all austenite or all martensite. But nevertheless, nature chooses the minimizing sequence. Okay, so that's quite surprising. I mean, if you do usual calculus of variations and you found a minimizer, you wouldn't then say, okay, maybe I should go back and look for the minimizing sequences of this energy too. You don't usually do that. So, of course, the material has to get from austenite to martensite somehow. And so probably that plays some kind of role. But anyway, from a mathematical point of view, it's quite unusual. Another thing that's somehow wrong about the analysis I just presented was it got all the geometry right. I described the normal, but all the other geometric features, including the volume fraction to high accuracy, are given by that calculation. It doesn't give, it somehow says that the microstructure should be infinitely fine here, and it's got a certain fineness, right? So it's another thing that we have to think about. And people have thought about this. I'll tell you more about that in a minute. Let me first say a little bit about the algebra. I said that if you get everything right, this m and so forth, you can drive the energy in this transition layer to zero. The conditions are actually that the average deformation, for that to occur, the average deformation gradient, which is written here, of this laminate has to be compatible with the identity. So it's a very simple condition. It's the average deformation gradient of this. You take the average deformation, you take its gradient, it has to be compatible with this. That kind of makes sense, right? That should be the condition under which you can drive the energy in this transition layer to zero. Okay, and then we're going to talk about the solution in a little while, but that's for now. Okay, we go back to recall the notation. I hope you recall it. So now we can do now that we know more about minimizing sequences, we can do some more diagrams. So here's the diagram which goes with this microstructure. So this A and B differ by a rank 1 matrix. So again, you start with A, and it has two rank 1 connections. You choose one of them. And this equation that I just showed you here, which is the condition for being able to drive the transition layer energy to zero, is, if you see this, it's just a convex combination. So in fact, that equation represented in symbolic form is that there's a point along the line between A and B which differs from identity by a rank 1 matrix. Okay, that's the condition. So that's the algebra of those equations written in pictures. So you basically find a rank 1 connection. You do have to there was a free rotation. That's also free in the calculation, and then you take the line between those and you look for a rank 1 connection between that and the identity. If you do, you get this picture. Okay, so there's the algebra. Here's another picture in this is the same copper, aluminum, nickel alloy. And this is next one I'm going to show you is a microstructure which just consists of these two variants. We see it when we transform the crystal, and then we apply stresses to get rid of, particular stresses to get rid of all the other variants except variants 1 and 2. And we see this microstructure. It's been studied quite a bit as well. And you can really see that microstructure is essentially governed by the same mathematics as the austenite-martensite interface. So these are two variants A and B. They differ by a rank 1 matrix. So once again, what you do algebraically is you start at A, and you look for, A has two rank 1 connections. You choose one of them, and then you take something on the line between A and B. Lambda, or FA times 1 minus FB, that's that point, and you look for a rank 1 connection back to this well, or back to this well. And indeed you find one, exactly one. That's this A prime. And so there should be, I can drive the energy in this transition layer to zero, I can write a minimizing sequence, and that's the physical realization of that minimizing sequence. The volume fraction here will be correctly predicted, and so forth. In this case, actually, you can vary the volume fraction. So you can vary that point, and at every choice, there's exactly one matrix over here, which is rank 1 connected. That's also seen in experiments, the fact that you can vary the volume fraction here. And this interface changes a bit as you vary the volume fraction. Here's another one, which is going to be very relevant to the next discussion, is the following. So this is a microstructure we see in that material, this copper aluminum nickel alloy. It's a wedge. Now, I hope you're getting good at this, because we can just look at this picture and figure out what the rank 1 connection should be. So there's an austenite-martensite interface. It's going a little bit out of focus there, right there. So that should be governed by a matrix here and here which differ by rank 1, like this line, and then a point along that line should differ from the identity. We already discussed that. That's austenite, and indeed that happens. And this one should also be governed by some calculation like that. So again, C and D differ by rank 1. A point along the line differs from the identity, and so forth. But then again, there's this interface. That's an interface between two laminates. So that should be governed by a rank 1 connection between some point along this line and a point along this line. So you start searching. You take a point along this line and you search for a point along this line that differs from that point by rank 1 matrix. Okay? You find that there's an exceedingly small gap. So that it doesn't differ by, there's no point, you take the measured lattice parameters of this material, there's no point along this line which differs from this point, from any point over here, by a rank 1 matrix. But it almost, it's, as I say, it's very small. That microstructure was so characteristic of copper, aluminum, nickel, it was put on the cover of this book. But let's plot this in a different way. So this is a diagram. Remember, this alloy has 3 lattice parameters, alpha, beta, and gamma. So in this diagram, I'm putting beta equal to the measured lattice parameter of the alloy, and alpha and gamma are the other 2 lattice parameters, okay? And if this had no gap right there, if there was a perfect rank 1 connection, we would be on one of these lines. The reason there are dashed lines and there are several lines, there are various cases. You remember I could take A, have 2 rank 1 connections, and C, there's various choices, and that's represented by these lines. So the bottom line is, theoretically, if you put beta equal to 0.9178, and you lie on one of these lines, then this can be represented by an energy minimizing sequence. So that dot is the measured lattice parameter alpha and gamma of this alloy. And when this happened, I asked Kevin Hain to plot it again more closely, and he went closer and closer. So it's exceedingly close to being on this line. So that's a case of it's not given by symmetry. It's given by special lattice parameters. There's a special choice of lattice parameters, and apparently the measured lattice parameters of this copper, aluminum, nickel alloy are close enough that this can be considered on that line, and we see this microstructure all the time. Okay? But it gives you the idea that, now wait a minute, I can start tuning the lattice parameters of this material to make conditions of compatibility satisfied. Okay? So that's going to be a theme going forward. Before I do that, I want to say a little bit about branching. I said there was one thing that minimizing sequence got wrong about this. It's not infinitely fine. There's a second thing it gets wrong. If you look very carefully, I don't know if you can see back there, that there's a band, but there's another tiny band there that's just starting. And then there's another tiny band there that starts there, and there's another tiny band there that starts there. In other words, this is branched. This is actually a branched microstructure. And explaining that has also been a very interesting theme. Okay, there's simple models. Bob Cohn and Stefan Müller introduced the first one. And they noticed that under certain assumptions, you could get a better scaling of the energy than with the naive construction that I presented with the transition layer. These models, recently these models have been made more realistic, partly due to the work of Chen and Conti and partly due to Hunter Steiner and Paul Klaczynski. But in any case, this branching can also be explained, and this is a kind of realistic test function in copper with the measured parameters of copper, aluminum, nickel, and moduli and so forth of the branched microstructure. The role of the branched microstructure is that you remove the transition layer. The transition layer that we originally constructed here gets delocalized. So the elastic energy is over a much larger region, and but still the the predictions of volume fraction and the normal of the interface are the same. So the close relation between the two calculations. In any case, and now getting to the point about hysteresis, is there's something that either all of these models are the model without interfacial energy. So these models have an interfacial energy term, so they have a penalty for the boundaries. And that's going to play an important role in hysteresis. And let me explain why. So imagine that you're in, let's go back to maybe the more simple picture. There. So you imagine you're in the austenite phase. You're all red on your crystal. And you're at high temperature and you're cooling the crystal, and you reach the transition temperature, this theta C, where the wells are at the same height of the austenite well and martensite. And now you're continuing cooling a bit, and so the martensite well is getting a bit lower. What you would expect to see is one of these interfaces move in. But now if you think about it, then there's energy penalty in this more realistic set of models. There's an energy penalty to having these interfaces move in, because there's the interfacial energy on these bands. Because it's not infinitely fine, there's interfacial energy on these bands, and there's bulk energy, either delocalized or localized, in this transition layer. And so this bulk energy picture with this lower energy well, there might be a penalty to going to this other energy well, because in order to get there, you have to create an austenite-martensite interface. It has additional positive interfacial energy. It also has some bulk energy because it's not infinitely fine. Okay, so there's sources of energy which are not in the most naive calculation that I presented that could make an energy barrier which prevents transformation. Okay, so that's so hysteresis could be related to metastability. Transformation could be delayed because the additional bulk and interfacial energy that must be present merely because of the coexistence of the phases has to be overcome by a further lowering of the energy well of the stable phase, as I described. So that's something one could study, and we studied that, and I'll show you a little bit the theory of that a bit later. But also, from an experimental viewpoint, is there something immediately you can do about this, right? Because, you know, if there's a barrier set up by the additional bulk and interfacial energy of coexistence, why don't you just get rid of that interfacial energy and this bulk energy? How do you do that? You use the lemma. You make the austenite phase perfectly compatible with the martensite phase, with a single variant of the martensite phase. Okay? And how do you do that? You make the middle eigenvalue of this matrix, this is the transformation stretch matrix, which maps one crystal structure into another. You make the middle eigenvalue of this matrix equal to 1. So the experimental test is, now this matrix, these are all non-stoichiometric alloys. So this matrix doesn't depend strongly, but depends on the composition of the alloy. So you could measure lambda 2, the middle eigenvalue of this matrix, change the composition, measure lambda 2. You could try to make it closer and closer to 1. Okay? So in fact, we did that. And the results were astounding, actually. These are measurements of hysteresis. The first measurements were actually done in my little lab, and we did those measurements. We saw this incredibly sharp drop. Later, people who do combinatorial synthesis did it. So this is a graph of hysteresis versus middle eigenvalue. Each of these markers is a different alloy with a different composition. And they've all been replotted in this way versus the middle eigenvalue, and this is the measured hysteresis of the alloy. And so you can see there's many alloys down here. They're in this nickel titanium X, Y, Z system, and even down near here, you could make alloys with near zero hysteresis by changing the composition to make lambda 2 equal to 1. Okay. So this alloys are some of the most studied alloys in all of material science, In fact, they are these days, nickel titanium X alloys are the most studied alloys in all of material science. And so how did people, people made, this was fairly recent result, maybe less than 10 years ago. How did people, miss the fact that people are always interested in hysteresis. How did they miss the fact that it drops down so suddenly here? It's because it's incredibly sensitive to composition. So when they made their alloy series, they always jumped across this singularity. Okay? So it really shows the importance of having a mathematical theory. Really, that's the key lesson here. And especially if there's a singularity, you just may not notice it by making standard alloy series, not guided by some theoretical results. Here's some details about that. This is tuned. We used to think, actually, this has lambda 2 very near 1. I'll show you something about that in a second. I see also I'm running out of time. I'll go to 11:10 maybe, leave 5 minutes for questions. Is that okay, Peter? Yeah. Okay. This is a high-resolution picture of an exact interface between austenite and martensite in titanium nickel palladium, and the measured normal to this interface is 7 minus 5. That agrees very well with the N, and the lattice rotation is 3.8 degrees. That agrees very well with the angle in Q, so you can have a nice agreement between the theory and the experiment. This is nickel titanium palladium. As I said, we used to think that was the lambda 2 equals 1 alloy. And then we started changing composition by 1/4% increments, and we got it down to 2 degrees hysteresis here. And the reversibility of the phase transformation, this is a calorimetry graph, also improved quite a bit, just going from here to here. So all these things are incredibly sensitive to composition. So this is back and forth, heating and cooling and measuring the latent heat, essentially. This is the heat flowing into the specimen, the rate of heat flow into the specimen. And if you look closely, there's a migration of the transformation here. And this is lost when you make even one of these high resolution changes from 10.75 to 9.25. So, okay, so I think that's a good place to stop. And I can take a few questions here.
Maybe this is a good question. How do you change the volume fraction of the variance in the lab? And how do you set lambda 1 to be 1 in practice? Lambda 2
in practice, okay, lambda 2 to 1 is, let me answer the second question first. To make lambda 2 equals 1, you have to measure, the details matter. Measure very accurately the lattice parameters. And that's done, you take your specimen to the X-ray machine, and you get, you do what mathematically is, as Mitch described, Fourier transform, and you look at the peaks and accurately measure the peaks, and you work back to the lattice parameters. So that's, and you take your first alloy to the lab, to the X-ray machine, and you measure, and you do it as accurately as you can, and you find that you calculate lambda 2, it's not 1. But of course, it's not rocket science just to now you take your second alloy and you, with a little different composition, you do the same thing. Lambda 2 either gets closer to 1 or further from 1, and you just march by changing composition. Of course, during the process, you're developing the mathematical relationship between lambda 2 and composition. Or lattice parameters and composition. That's a surface. So you're developing you're developing that surface, and so you can use some approximation methods to get that surface. But it's, as I say, it's not sophisticated at all. In practice, what we like to do is we like to have a composition in which within experimental accuracy, we have lambda 2 slightly greater than 1, and another alloy with slightly less than lambda 2 slightly less than 1 within experimental error bars, and then we interpolate the two compositions. So really, one tries very hard to get this exact composition. And so it matters, actually, yeah. Yeah. Yeah.
You talked about the branching. I was just interested to know how well you understand that fine scale structure. Whether you understand what the wavelength or the volume fraction of the function position.
Yeah. Okay. In some. Okay. Explain is a hard word. Okay. So the latest work is the work I mentioned here. There's a. So explain means the following. It means that there's a test function, which agrees there's a plot of the test function, agrees very well with this. It has the same energy. It has the same energy scaling. It has this good energy scaling, but since we don't know the constant in the energy scaling, there's not a precise relationship between the test function and the lower bound. So the test function, is consistent with the upper bound. There's a lower bound which is obtained by theoretical methods without assuming any geometry. The test function is very reasonable in the sense that if you embed it in a 1 or 2 parameter family of related test functions, it's the best one. So it's not perfect. I mean, the answer,
You can't say what the fine scale structure is as a function.
Yeah, well, no, that's given, and that's in fact we believe this could turn out to be the best method of measuring the interfacial energy constant of So it predicts the scaling not only of the energy versus the parameters, but also the scaling of the doubling of the interfaces as a function of the distance from the interface. This is also given by the test function, but also consistent with also a theoretical bound. But again, the constant in the theoretical bound is not known. Yeah. So we think this is quite a good test function. It's been optimized in the best we can do as a test function, right? Sure.